Hi everyone, I'm Adyasha Mohanty, a graduate student in the Department of Aeronautics and Astronautics at Stanford University. I will be presenting a particle filtering framework for tight GNSS-Camera Fusion using convolutional neural networks. In urban environments, we have access to a variety of sensor modalities such as GNSS, camera, radar, and LiDAR. Usually, these sensors suffer from measurement faults due to different factors. GNSS, for example, suffers from reflections due to presence of tall buildings, as well as non-line of sight errors. Vision can suffer from errors due to changes in illumination as well as occlusions. In order to provide reliable positioning, we need to mitigate these measurement faults. There are some challenges, however, in this process. Usually these faults are multiple and heavy-tailed in nature. They do not obey standard error models or follow standard Gaussian assumptions. And lastly, they are hard to mitigate while estimating the state simultaneously. Let's take a look at some of the prior works that have addressed fault mitigation in urban environments. These works can be categorized into two approaches. The first category of works deal with Kalman filtering or one of its variants, such as the EKF, UKF, or information filter. They are usually combined with a more traditional method for fault mitigation. For example, RAIN, that is classic to the GPS or GNSS community, KL divergence, that is used to assess the consistency between the predicted and the updated distribution, and finally M estimator, which is an optimization-based technique. Note that these approaches have the following limitations. They usually assume linearized measurement models, only output point-valued positioning estimates, and finally, address state estimation and fault mitigation in a sequential manner. The second category of works use factor graph optimization method. Usually, these methods have also been combined with M estimator for fault mitigation. But note that similar to the prior works, they also only output point-valued positioning estimates and not probabilistic estimates. This is the outline of my talk today. First, I'll provide a brief background on joint state estimation and fault mitigation. Then I'll talk about the proposed particle filter framework along with the two main modules. Then I'll provide results on experimental validation on real-world dataset. And finally, I'll conclude my talk. The overarching concept is based on joint state estimation and fault mitigation. In this, we use a particle filter that lets us track multimodal state probability distribution, and we address measurement faults, mitigating multiple measurement faults, and estimating the state in a unified framework. Let's start with traditional RAIN, where we receive pseudorange measurements from about 3 to 4 satellites. Note that the first 3 satellites are correct, and the last one is faulty. We use all measurements to compute the first positioning solution, and then using the consistency of the pseudorange measurements from the faulty satellite across all of the pseudorange measurements, we can then isolate the faulty one, and finally, recompute our position. In particle RAIN, however, instead of outputting a single point-valued positioning estimate, we have a distribution or collection of particles where each particle represents a position hypothesis. Additionally, each particle is associated with a subset of measurements. Based on a voting scheme that is inspired from traditional RAIN, we can then assess the correctness of each of these GNSS measurements. Finally, we can form or capture the state distribution using a Gaussian mixture model likelihood. Note that in our prior work, we extended particle RAIN to incorporate additional measurements from vision. In this regard, we derived a probabilistic metric, but before that, we first designed a camera measurement likelihood using the classical method of image registration. Then we used the coarse estimate from GNSS measurement likelihood to assess the correctness of the camera measurement likelihood. However, our prior work only loosely coupled GNSS and vision. Furthermore, it assumed that the GNSS likelihood was coarse but correct, and then used that to reinforce or find out the correct vision measurement likelihood. Our prior work also used image registration that turned out to be expensive at inference time, required access to a database of images, and was usually less robust to typical vision faults. In this work, we tried to tightly couple GNSS and vision, where we use vision to mitigate GNSS faults, and we use GNSS to mitigate vision faults. Note that our work does not assume the correctness of any measurement likelihood, unlike our prior work. Instead of using image registration, we now propose a data-driven method using convolutional neural networks, or CNN. This helps us to completely get rid of the measurement likelihood that we had in our prior work, and is also faster at inference time and more robust to vision faults. Next, I'll describe the overarching framework and the two main modules. The framework achieves tight GNSS-Camera Fusion, whereby we optimize the particle weights that jointly minimize both the GNSS residuals from pseudorange measurements and the camera residuals from candidate poses. Here, candidate poses refer to the output of the proposed data-driven CNN module. Then, within the optimization objective, we use an M estimator to mitigate multiple measurement faults simultaneously while estimating the state. This is depicted in the figure below, where we have a collection of particles that represent our position hypothesis, and we have access to a variety of pseudorange measurements as well as camera measurements. After performing fault mitigation, we can then reduce or de-weigh the impact that these faulty GNSS and camera measurements have on the overall positioning solution. Our key contributions include designing a particle filter framework for tight GNSS-Camera Fusion, designing a convolutional neural network-based camera module that infers candidate poses from images with low computational overhead, and finally, treating state estimation and fault mitigation jointly with an M estimator that helps us mitigate multiple GNSS and camera measurement faults. Our framework is shown here with the red modules being the two big modules that I'll describe. First, we start with an initial particle distribution and then motion data from I. That is computed in the propagation step, where we can then output the particles that represent a position hypothesis, and they are passed to the tight GNSS-Camera Fusion module. In parallel, the GNSS module takes in raw pseudorange measurements, probably from multiple satellites. Using this data, as well as IMU, we can then synchronize the camera measurements along with the GNSS measurements. The CNN-based camera module also receives camera images and outputs candidate poses that are fed to the tight GNSS-Camera Fusion module. Note that this module also takes in the expected ranges from the GNSS module, and then utilizing the information that it has from GNSS and camera, as well as the particles, it can then compute the optimal particle weights so as to minimize the joint residuals from both sensors. Let's talk about the CNN-based camera module. Note that our goal here is to infer the candidate pose from a single camera image. Existing CNNs, however, are usually bulky and expensive to train because they have a lot of parameters. There are some lightweight CNNs, such as SqueezeNet, that exist in literature, but they have only been explored for classification tasks and not for the intended task that we want. Challenges of using this architecture as it is that the accuracy can be compromised when we are directly trying to train it on new tasks. And this requires us to build or perhaps train the architecture on newer datasets to prevent overfitting. How do we then design a lightweight CNN to generate candidate poses with high accuracy? Well, we retain the compact size of SqueezeNet that exists in literature with 5 modules. The 5 modules are a series of 1x1 and 3x3 convolutional and pooling layers that are stacked next to each other. Additionally, we replace the final layers of SqueezeNet with fully connected layers that helps us regress the candidate poses from raw images. To prevent overfitting, we also apply dropout before the last layer. This architecture is trained on various urban environment datasets using a Euclidean distance loss function that minimizes the distance between ground truth and candidate poses at every time we work. Finally, let's talk about the tight GNSS-Camera Fusion module. Here, the goal is to create residuals from GNSS pseudorange measurements and camera candidate poses. As an objective function, we use a classic example in the M estimator family, such as the Tukey biasquare loss. We also include a loss balancing factor that enforces tight coupling of both GNSS and camera sensors. The objective is shown here, where the unknown that we are trying to infer is this vector that consists of the particle weights. We are trying to minimize the residuals from GNSS measurements as well as the camera measurements. And you can observe the loss balancing factor that is sandwiched between both sensors. The example loss function that we use is given here. Again, this is from the 2-key biasquare loss family, a classic example of an estimator. The goal is to jointly optimize the residuals from GNSS and camera while mitigating multiple measurement faults so as to infer the optimal particle weights. These particle weights then go on to form the particle distribution, the mean of which gives us the overall positioning estimate at one time epoch. Next, I'll talk about experimental validation of our framework on real-world dataset. Our dataset is a 2.3 kilometer driving dataset that was collected in urban Frankfurt. It consists of eco-motion data from IMU, pseudorange measurements from multiple GNSS constellations, vision data, as well as ground truth from a high-quality commercial GNSS inertial fuse system. The dataset contains natural faults because we have about 32% of non-line of sight errors in GNSS, as well as vision errors due to varying illumination across images. We also induce additional faults in the dataset for stress testing our algorithm. For GNSS, we add Gaussian bias noises to random pseudorange measurements. And for vision, we add Gaussian blur and occlusions, as shown here in the example, to random images as well. Our experimental parameters for the particle filter are given here. Note that the state here is a 3D vector computed in the ECEF coordinate frame. And we have about 2 to 9 GNSS satellite measurements, where we have about 12 measurements, out of which 2 to 9 are faulty. And then we have about 50 to 100 meters of added bias to these measurements. The parameters for the CNN-based camera module are shown here on the right. Note that we train it using the classic Adam optimizer using an NVIDIA GPU for about 200 time epochs. As baselines, we use sensor fusion particle ring with loose GNSS-Camera coupling, which is our prior work from last year. We also test our algorithm where we retain the tight GNSS-Camera coupling approach, but instead of using our proposed CNN, we use a baseline CNN that is dense and contains more parameters and errors than our CNN. For metrics, we use the positioning error as a function of time. We study the distribution of positioning error, as well as the root mean square error, or RMSE, of the positioning estimates. Here we show 2 example scenarios for testing our algorithm. The first scenario considers low number of faults, where we have blurred images as well as occluded images, and we have about 2 satellite faults with 200-meter added bias to the pseudorange measurements. We first look at the positioning error as a function of time, and notice that the error does not progressively increase with time. We also take a look at the positioning error distribution, and notice that our algorithm can detect and mitigate low number of faults, where about 95% of the errors are less than 5.6 meters. We also perform sensitivity analysis of our algorithm over different added bias values, and then compare the results with other baselines. From this plot, we observe that our proposed tight GNSS vision coupling is able to produce lower error than loose coupling across all cases. Furthermore, in most cases, our CNN outperforms the baseline CNN, even though it consists of fewer parameters and layers. Moving on to example scenario 2, where we test our algorithm with high number of faults. We retain similar kind of faults for vision, but for GNSS, we increase the number of satellite faults from 2 to 9, and then decrease the added bias from 200 meters to 100 meters. Again, the positioning error shows that the error does not progressively increase with time, and the error distribution on the right indicates that our algorithm can detect and mitigate high bias values at relatively high number of satellite faults, since 95% of the errors still fall less than 5.82 meters. Similar to the scenario 1, we perform a sensitivity analysis over different bias values. Looking at the plots, we can see that our algorithm still produces lower error than loose coupling. And for most cases, our CNN can outperform the baseline CNN with fewer parameters. The overall error across all cases, considering scenario 1 and scenario 2, remains less than 8.5 meters. Finally, I'll conclude my talk. In this work, we designed a particle filtering framework for joint state estimation and fault mitigation. We tightly fused GNSS and camera while mitigating multiple measurement faults using an optimization approach within particle filter. We developed a CNN-based camera module to infer candidate poses from raw images, and we experimentally validated our framework on real-world urban driving dataset with natural and induced GNSS and vision fields. We would like to acknowledge Ford Motor Company for sponsoring this work, as well as other members of the NavLab for their feedback. Thank you.